Okay, let's continue with on our trip to through cryptographic primitives for privacy-preserving computation. So we saw in the first part, we saw the secure multi-party computation and fully homomorphic encryption. Now, often you also want to do some kind of zero-knowledge proofs. You want to prove that you actually did something without revealing what you actually did. Which sounds again like a typical cryptographic thing that you often do. So we always suppose that we have some prover that wants to prove something. And we have a verifier that the prover wants to convince. So there is a very simple example here with if you have two balls of a red and a green ball, and we have somebody who only sees black and white. Okay, so he has this color blindness, he only sees black and white. And I want to convince this person that, in fact, the two balls are different. So, of course, the person will tell me, well, no, you're not. You're just saying anything. And I say, no, I can prove that the two balls are different. And what I will do is I will say, okay, you take the two balls, and then behind your back, you swap them as much as you like, but remember how you exchanged them. And you give me back the two balls. And I will be able to tell you which one is the blue and which one is the green one. And because I told you before, and you know how you swapped them, you know whether I lie or not. Okay? So I do that once. And then, of course, the person might say, well, you just got lucky. Okay? So you just got lucky, 50% chance, so he does it again. And again, I tell him this one here is the blue. And because he knew how he swapped the balls, he knows, okay, in fact, it's the same as before. So in the end, if I do it enough times, I can convince my friend that indeed there is something like colors. And my friend in the end will have to say, okay, yes, true, there are colors. Even though I don't see them, I do believe that you see these colors. And so he will know that I did not lie to him. These are called interactive zero-knowledge proofs, where you interact, so where the prover and the verifier interact. But in recent years, there have been a whole set of zero-knowledge proofs that are in fact non-interactive, meaning that the prover just creates one data set, and he can send that to the verifier, and then the verifier can look and see that indeed the prover knows something that they agreed upon before, but doesn't know exactly what. So some examples of real life, what you can do with zero-knowledge proofs is, for example, if you have a bank, and the bank wants to prove to the state, for example, the government, that the total in his accounts is $12 billion, or 12 bitcoins. Oh, it's perhaps bitcoins here, huh? He wants to prove that the bank has 12 bitcoins, without giving out each and every account. Because, of course, there are big, rich people who put their money in this bank's account, and they don't want to give away who has how much money. Now, with a zero-knowledge proof, a bank could typically prove that the sum of all its accounts is, in fact, 12 bitcoins, without revealing each individual account. And then the verifier could say, okay, I see that, in fact, you do have all these accounts, and I see that, obviously, they sum up to 12 bitcoins, so it's okay, you are entrusted with 12 bitcoins, and go on and sell those 12 bitcoins however you want. Another problem is often in the blockchain world, where you have these big exchange websites that say, okay, you can buy a Bitcoin at my place, and then you can sell it again, and so on. Often these sites, you don't really know whether they have all these Bitcoins or not. You're not sure whether they really have Bitcoins, or whether they just say, well, I sell you Bitcoins, and then you can sell them again. That could also be a scam. So zero-knowledge proof could also help to prove to these exchange sites that they have, in fact, these bitcoins. Charging customers for energy consumption. So again, as a good paranoid cryptographer, you don't want to give away your energy consumption, you don't want to say how much energy you consumed, because they might learn that you have some special plantation in your place, they might learn that you are on vacation, they might learn how much people you have in your household, they might learn all kinds of things from your energy consumption, they might learn when you get up in the morning, when you go to sleep in the evening, and all that things, and you don't want to give this away to the electric company. So you just prove to the electric company that, listen, I have this counter of electricity in my basement, and together with this counter we create a proof, together with the counter and the bank, I create a proof that in fact the amount I paid to your account is enough to cover my bill's expense. And then the electricity company can look at the zero knowledge proof and say, oh yes, okay, it's good, you paid all the electricity that you need to do, without knowing exactly how much electricity you used when. Okay, proving identity during authentication, so saying I am part of EPFL, I am over 18, I am male, I am female, I am, I don't know, my forename starts with A, whatever. You can create a zero knowledge proof, and then you can create it and send it to the verifier, and the verifier can make sure that it is like that without knowing what is actually behind. To have a good zero knowledge proof, you need three things. First of all, you want it to be complete. You want so that if the input is true, so if I want to prove that I'm over 18, that the verifier will be convinced. So that the verifier will say, okay, it's true, Linus is over 18, so he's allowed to get on this web page. You also want it to be sound. So you want it so that if the input is false, so if I say I'm over 50, that I cannot create a proof to convince any verifier that I am indeed over 50. So that is the soundness property. And finally, you want to have the privacy property, so whatever I prove on my age, over 18, over 50, or whatever, the verifier should not learn what my real age is. Okay, so the real age should stay only on the machine that knows my real age, but should not go to the verifier. So these are three properties that you need for zero knowledge proofs: completeness, soundness, and privacy. Okay, we have this. As you said, on blockchains, the normal blockchains, so Bitcoin blockchains, everything is in the open. So every transaction you do, it is written, this account paid this many Bitcoins to that account. You can read it all there. And the FBI and NSA, they in fact manage to match these transactions to transactions that you do on the exchange rates. And then usually if you try to get real money out of Bitcoins, then usually they know who you are. So this is something they try to do with the Silk Road. That was a website that sold drugs and other things on the dark web. And they managed to link some of the accounts, looking what happens in Bitcoins and who got all of a sudden a chunk of money on their bank account. So this is not very privacy preserving. So there is a way to, in fact, put transactions on the blockchain where we don't say anymore, I am sending this many Bitcoins to that person. But you say, I prove that the amount that I sent to this person is on my account. And you send this to the blockchain, and then everybody can verify that, in fact, you did send X amount, where X is unknown. Nobody knows what you sent, but they know that the amount you sent was, in fact, on your account and has been sent to a third party. And now Zcash here put it even so that you can have on the sender side, so where you get the money from, you can have it either in the open, so you can have it like in Bitcoin, everybody knows from where you sent it, or you can have it concealed, so hidden. And the same thing on the receiver side. You can say, okay, I want to give to this address, and everybody will see the address. Or you can do it with a zero knowledge proof and just giving a proof to the other party with which the other party can prove that he has some amount of Zcash, even though the verifier doesn't know how much Zcash he has, but he has this amount and he transfers it to somebody else. So it's a very nice system, the Zcash. Shielded transactions, they call it. Yeah, they have this shielded and transparent. Okay, I forgot the names. So transparent transactions are transactions that are visible, and shielded transactions are these zero-knowledge proofed transactions. Now, the big problem with these ZK snarks is, one of the big problems. Somebody already played with Zcash? No? What was the problem with secure multi-party computation with fully homomorphic encryption? Sorry? It's slow, exactly, slow. So to create a transaction on your computer, it takes like 5 minutes or so, if you have a fast computer. So just to pay something, your computer has to calculate for 5 minutes to create a valid zero-knowledge proof that can then be verified. I think the verification is faster. I think the verification only takes orders of seconds. But still, if you have a lot of transactions, if you need to verify and every verification takes 1 second, it's still a lot. It's still a lot. So this was a problem, and they worked on it, Zcash, and they managed to have some new zero-knowledge proofs that made it much faster. And now instead of 5 minutes, I think it still takes 20 seconds or so to create a transaction on your computer. And then you can send it to the Zcash network, and then it is verified. And if the verification turns okay, it is put in the block. So this is a very nice, they use this CK snarks, succinct, non-interactive argument of knowledge. So this non-interactive, as I told you before, this means you don't have to send, so like with the balls where you have to do it multiple times till the other party is convinced. Here you just do it once. You just send the result and the other party can directly verify it and make sure that it's correct. Okay, so there are some details here on Zcash. Yes, so they're working with these commitments, and once you have a commitment on the blockchain, then you can spend it with a nullifier. I have to admit I would have to read up again specifically how it works, but you always prove that you do have the money and without saying how much money you have, and so it is very privacy preserving because you can do all these transactions without without being visible where you sent how much money. So you could say, well, this is very good if you are from the mob, from the mafia or so, because all your money is hidden, but we would like to make it a little bit visible, but not too much. So there is a cryptocurrency that is not very visible. I'm not even sure it still really exists. That's called Thaler. And Thaler, in fact, they made something between Bitcoin and Zcash. So on one hand, everything is private, everything is hidden, but for the state, they have a special thing where they cannot see to whom you sent, but they can see how much you sent. So they can make some kind of tax and say whenever you transmit something, you have to pay some kind of tax to the state, and then the state still gets its taxes, so the state is happy, and you get your privacy, so you're also happy, and in the end, everybody is happy. So there are also systems where they kind of mix these different ways of being hidden and being a little bit open and still paying some taxes. So one system like that is Thaler. And I'm not even sure whether they also use zero-knowledge proofs, but they most probably must do something in that sense. Okay. So this was the third way of doing privacy-preserving cryptography. The last thing that I want to present today is the private information retrieval, which is a bit dumped down. So it gets always simpler. So secure multi-party computation, you can do anything you want, but it's very complex. I really need to turn that off if I come here, don't I? So secure multi-party computation, you can do any function you want, but it's very complex. Homomorphic encryption, you can do a little bit less, but it's faster. Zero knowledge proofs, you can just prove that in fact you have this thing without revealing what you really have. And private information retrieval is in fact just getting data without the server knowing what kind of data you wanted. Yeah, so this comes from the fact that we have all these different cloud storages. And can we trust the cloud? Of course, as a good cryptographer, we all have to shout, no, we don't trust the cloud. The cloud is evil. The cloud wants to watch us. The cloud wants to look what data we have. So we have this large attack surface because there are a lot of servers. They're all over the world. They are even in places like in the States, where the state, in the United States of America, where the government can come and have a subpoena and say, well, you have to give me your data, and you're not even allowed to talk about it. You can have bugs in there, malware. You can have just disgruntled employees like in the NSA, what was his name, Snowden, who took all the data and then just gave it out to everybody. Yeah, Big Brother, NSA, USA. And so a lot of people are encrypting their data, but problem is that encryption is not always enough. We have this access pattern that sometimes can give away the data. So I think probably Brian or me already talked about this Netflix attack. So if you just look at the download stream from Netflix, even if it's HTTPS, just looking how many packets per second you get, I can already infer what film you're watching. So this is, of course, something that we as good cryptographers don't want to do. So we would like to hide these access patterns, because these access patterns, in fact, can reveal what you do. For example, if you have some kind of stock trader who interacts with this untrusted cloud storage, if you can look at these access patterns, they say here, if you have an encrypted database even, you can reveal 80% of the search queries. So if the client looks what is happening with IBM stocks, the honest but curious, so this is a honest but curious setting, so the cloud server gives the data it's supposed to give, but it snoops and looks what kind of data it gives. No, I think it's not even the cloud server, it's just here on the network. So the network is honest but curious, so the network forwards packets, but it looks what kind of packets it forwards, and even though everything is encrypted, the network already can know what this trader is looking at, so the network knows what the trader wants to trade and then can short the stock or do anything just before the trader actually wants to do his trade, and then the trader loses money, and that's of course very bad because no trader wants to lose money. So we do have, of course, confidentiality, so we encrypt it. We want to have integrity, so we put some hashes, we can sign it, we can have a Merkle tree, whatever. We want it to be reliable, so we put multiple hard disks in there, we put it over multiple data centers. Proofs of retrievability, that's in fact a very nice one. Proofs of retrievability, I always think about backups. So if you're doing backups, that's very good, but what is even better is testing your backup that it actually works. And that's kind of proofs of retrievability. That means that not only your data is copied in multiple data centers, but you can prove that in fact the data is in multiple data centers. So like with backup, not only do you have a backup, but you can prove that your backup is good and that it works. Because only a checked backup is a good backup, an unchecked backup is not a backup at all. But so now we also want to have this access privacy. And there is the simple one, which is called the private information retrieval, PIR. That's kind of a read access. So I just say, okay, I want to have this column or this row in the data set, and the database server gives it to you without knowing what it gives. Or, more complex, you can do oblivious RAM. So oblivious, again, meaning that nobody knows what you're doing. So oblivious RAM means you can write and read. And so oblivious RAM is something very nice, where you can store things and retrieve them, and the server does not know what you store, neither where you store it, neither how much you store. It just knows it stored something somewhere, and you can retrieve it later, and you will get the data back. Yeah, there's a real-world example of somebody who is doing something very embarrassing. He wants to have information about the notebook. So that's very embarrassing. So he doesn't want the database storage to know, the database operator to know that he is interested in that movie, so he would like to be able to retrieve that movie from the database, so just the information, because if his friends find out, he's busted, okay? So, or perhaps his wife, I don't know, depends. Okay, so we want to protect the user's queries. Already in 95, the first proposition came how we can have some query to a database without the database finding out what we actually want. How can you do this? Well, there is a very simple solution to that problem, is we just download the entire database, okay? So every time you want to do a query, you just download the whole database. Good idea, no? Yeah, okay, yeah, everybody's good, okay, we're done. Of course, this is very costly. Huh? It's a big bandwidth overhead, so you don't want to do that. So you need to be a little bit smarter. So there are two possibilities to do this, either information theoretic or computational PIR, where you have different security. So in the information theoretic, you suppose that you have n servers and that only t out of n are malicious. I think it's n minus t are malicious. I think you have n server and t honest servers, t plus 1 honest servers. Sorry for that. Okay, so in the information theoretic PIR, you have n servers and t plus 1 honest servers. And in the computational PIR, you can get away with a single database server, and you can use homomorphic cryptographic techniques to then have this, have your privacy, and this, in fact, it's a very nice system. So for the information theoretic PIR, you have your database here. You have this one pixel that you want to download. So this is the notebook, that film that you don't want people to know, and you want to do it without downloading the entire database. So what you do is, let's say that the database is this matrix. So every D here is an entry for a film, D1 up to DR, and all the rest is zeros. Okay? And now you want to retrieve one element of the database. So you create your query here with all zeros, except the one here for this beta coordinate that you want to download. So you send your vector to the server multiplies the matrix with your vector, sums everything, and sends it back to you. Now, because you have zeros for all the D1, DR except D beta, if you sum up all the films you're not interested in, they will just be zeros. And you will only have the film you're interested in. Now, again, there's a problem with that scheme. What is it? Very simple problem, don't search too far. Huh?
It's a huge matrix.
It might be a huge matrix, but we suppose that here time is not a problem. Might be a problem, but here we suppose it's not. No. What can the server do? What can the server do if you send him that vector here? Exactly, you know the one, okay? So the server having this vector, he can say, okay, he's very smart, he wants me to sum up everything, but I know the one is here, I know he wants to see the notebook, okay? And you're bust. Okay, so that's not good. So we need to be a little bit smarter, so that's already got tracked into a little bit smarter, so we come with this Shamir secret sharing. Now, Shamir secret sharing is a nice thing of how you can distribute a secret with over t plus 1 parties. No, over more than t plus 1, over how many parties you want, but you need t plus 1 points. So let's say if we only have t points, this one here is one server has this point here, and now let's say a second server has this point over here, and then the secret is on the line that is drawn through these 2 points here, and this here on the y-axis. So the secret is always at x equals 0. So if t is 1, we have a polynomial of order t. So this is, oh, now I'm confused. Yeah, no, this is of order 1. So we need 2 points to define it. Okay, polynomial of order 1 is a plus bx. So we need 2 points to define it. And if we have 2 points, we get here the intersection with the y-axis, and this one here is our secret. Now what we can do is, instead of only having 2 points, we can make as many points on this line as we want, and we distribute this to all our servers. Okay? So as soon as t plus 1 servers, in that example, 2 servers come together, they can recreate the line, and they can get the secret. Okay? So any t plus 1 server can recreate the secret, but I can distribute it over n servers. And you can do the same thing with t equals 2, so for a polynomial of order 2, but then you need 3 points, for a polynomial of order 3, but then you need 4 points to define your curve, and then you always get the secret here on the y-axis. Now what we do is we take our vector with only 1, and we change it, so we Shamir secret share it, so that the sum of it gives our desired vector with only 1, and all zeros otherwise. But to each server, we send vectors that have 1s and -1s in other places. So each server, if he looks at the vector, will say, oh, I don't know which one he wants. There are 1s and -1s in multiple places. And only then, when I retrieve the replies from different servers, can I recreate the reply. So I need t plus 1 replies from, so I have n servers. Oh, here it's L. Why is it L? Oh, they changed the variables here. So let's say I have n servers where n is bigger equals t plus 1, and as long as I get t plus 1 replies, I can recreate. Now this supposes that t plus 1 servers don't collude. If t plus 1 servers collude, they can again find what film I'm looking for. But here I suppose I have only t servers colluding and not t plus 1. And then they cannot recreate the secrets, only I can. And then we can go further and say, okay, it's not only about colluding servers, but it's also about servers that might be down. So the servers, they might also be offline or so. So you can also say that we can turn it into a robustness problem, then how many servers responses we need to receive and still be able to recover. Well, as long as we have t plus 1 responses, we can still recover the data of our film. Okay, yeah, that's it. And then, okay, you can go on and you can, even if some of the responses are wrong, you can do some fancy Reed-Solomon things, and then even if you have some malicious server, you might still recover the secret. Yeah, so this is the total. So K, what I called N. So as long as you have N minus T minus 1, faulty servers only, you can still recover your database record. Okay, now the other possibility with using homomorphic encryption is if you have only one server, you can do the same thing, but now instead of sending zeros and ones, you send encrypted zeros and ones. And because you have the principle that if you encrypt twice 0, you get two different ciphertexts, the server does not know what is a 0 and what is a 1. So the server just sees a number of ciphertexts, and now he needs to take this number of ciphertexts, multiply it against his matrix, and make the sum. And because we are in a fully homomorphic scheme, where we have multiplication and addition, we can do this. And every time we multiply with a 0, well, it will just get 0, but it will be encrypted. The server will not know it's an encrypted 0. And only where we have a 1 will we get back the data that we want. And if we sum it all together, the zeros, they will just be ignored, and the 1 will be returned to me. So this is just a very simplified way of thinking how you want to do it. Now then, of course, this is only valid if you have a single number. Now, if you want to have a whole data set, you need to be a bit more smart about it. If you have big text or so, you need to make it better. But the basic intuition is that you can encrypt your zeros and ones, send it to the server. He does all the calculation in fully homomorphic encryption and sends you back the result. And you're happy, and one server is enough. And the server, even if he is as long as he is honest and curious, he will not be able to know what you wanted, even if he's curious. If he's malicious, you only will get back a garbled result, but he will not be able to know what you looked for. Okay. Yeah, so they use this quadratic residual assumption. Yeah, sorry. You can also do it with elliptic curves. I know these better. Okay, so PIR, we can protect the database so that all the queries that are run against this database, they are in fact protected in an honest but curious setting. So even if the database manager is curious, he will not be able to infer what you looked for. And we can have it either computational, so using homomorphic encryption, or information theoretic using this Shamir distribution, Shamir's shared secret. But we have very substantial overhead. Oh yeah, there is one use case of this PIR, which is in fact the not the EPFL voting, the Geneva Swiss voting. So there is in Switzerland, they want to have electronic votes now. They have them for a couple of years, but they're really trying to get them out. But as Switzerland is, they go very slowly, step by step. I think it's a good approach for something as complex as electronic voting. And in electronic voting, you have different things that you want to do. So you want to have cast as intended, means that you want to be sure that if you vote for this or for that people, that your cast has in fact, that your intention has been correctly cast. And then you want to be sure that it is recorded as cast, and you want to be sure that it's counted as recorded. So these are three things that you want to be sure, and you want, of course, have privacy on all the voting. Now, the last three are quite easy. So anonymity, counted as recorded, and recorded as cast, that's quite easy. But one difficult thing is always the recorded as cast. No, cast as intended, sorry. It's getting late, yeah, nearly done. Cast as intended, that's always a difficult part, because how can you be sure that what you wanted to vote is in fact what has been written to the database? Even if you can have a look at the database, let's say we have some kind of blockchain technology, and you are able to look at the database and you can verify that your vote has in fact been in there, because it is encrypted and you don't have the decryption key, you cannot know what is written in there. So you have to trust that the program on your computer encrypted your vote correctly and sent it correctly to this database, whatever it is. Now, the people from Geneva, they did something very nice, I thought. They used, in fact, PIR. And now what they do is, before the vote, well, they need a secure server that they trust. They need to have a trusted database, at least at the setup. And at a trusted database, they say if Linus wants to vote for I don't know, for Somaruga, if Linus wants to vote for her, then the reply will be this number. And they put that in the database. Now, the database should not know that I voted for Somaruga, but the database should still be able to give me back that number if I voted for her. Now, they solved this with this PIR, and they made it so nice that when I go to the website to vote, I enter my vote, and then the website encrypts my vote and sends it to the Geneva e-voting thing. So this thing is stored there. So I can verify that this thing is stored. And now this same encrypted thing can be used as a PIR, as a private information retrieval. The same blob, the same encrypted thing can be sent to the database, and the database does its fully homomorphic encrypted magic and gives me back the number without knowing for whom I voted, without knowing what the number represents. And because I got a sheet of paper in my mail, snail mail, I can look, okay, Somaruga, that's 1, 2, 3, 4, and the PIR database returns the 1, 2, 3, 4, and I can compare the two, and I can be sure that my vote has been correctly recorded as cast as intended, and then recorded as cast. And this is a very, very nice application of PIR. Yes?
At the same time, while you have this property, you can be like, you can sell your votes, right? I know that there's also another property which seems that collides with this.
Yeah.
And it's like, you cannot prove that you voted for someone. Because if you can prove that you voted for someone, then you can just simply sell your vote. But if you cannot prove, then no one will just give you money for voting for him, right?
Yes, yeah. Yeah,
so,
yeah.
Yeah, but I think it's colliding.
Yeah, then I think you will not be able to do that, yes, yeah. Or you should not be able to do that, yes, yeah, yeah. It can, in fact, it's in fact in both. So either you sell your vote or you could be coerced to vote.
Could be?
Coerced. So somebody putting a gun to your head and say you need to vote for Somaruga.
Yeah.
So yeah, you have both cases that are bad, yes. Yeah. But then, of course, if you have this, then you cannot have the other. Yes, yes. At least not using this PIR. Yeah. Exactly. Yeah. Okay. Yeah. So this PIR, this is something that is used slowly, but it is useful and it's good. Okay. So as conclusion, as I said, these are these 4 cryptographic things that you can do to have privacy, some kind of privacy in your data. Secure multi-party computation would be kind of the gold standard, but it's just too expensive for the moment. So as soon as you have more than a couple of hundred data points, it's just impossible to do. It's very nice. It's really very nice. It's superb theory. It's great, but it just got completely killed by SGX. I mean, it's just, yeah, it's just so slow. Homomorphic encryption is already useful like Unlinks or others. They're using homomorphic encryption. That's good. Zero knowledge proofs also. That's a very useful tool that you can prove that something that you have something or that some function verifies to your data without revealing your data. That's useful. And finally, PIR, yeah, as I said, in this Geneva CH vote project is used there. And this is something that is fast. Well, there is some overhead, but it's quite fast and it's secure and people start to know how to use it. Okay. Any questions on that part? No? Okay. Then have a nice evening and yeah. Nice exercises.